is here from Kitware. He is actually located on the East Coast, but we were lucky enough that his trip coincided with a conference he's participating on this week, and he was gracious enough to spend his last evening here with us. He is a technical lead in Kitware. He works with a project called Open Chemistry, and he develops there several tools or open source tools for visualization and working with their data. Today he will talk a little bit about those tools and the applications to visualization.
Thank you. Well, thank you for inviting me, and thank you to everyone who stayed. I'm going to talk a little bit about Kitware. It's an unusual company, but I'll be as brief as I can. I was founded back in '98. Right now there are around 120 of us, and there's quite a lot of PhDs in the company. It's a big mixture of different backgrounds, so I come from a background in physics, but we have a lot of computer scientists and electrical engineers and other things. And we have 4 offices dotted around the US, and 3 offices in the US and 1 in France. We work with lots of different clients from kind of academia, national labs, as well as a lot of commercial companies, but most of them don't like us to tell you who they are. But we do quite a lot of work on the back end for them. And we work in a lot of different domains. So I tend to spend most of my time in supercomputing visualization, but we do a lot of work in medical computing, medical imaging. Computer vision, video analysis is another major part of Kitware, and then the whole data management, and right in the middle is something I spend a lot of time on in software process. How do we make C++ and C code build everywhere, and how do we make that work seamlessly? Everything I'm going to talk about is open source. Normally it's BSD licensed, so it's very liberal. It's easy to integrate into commercial products if you want to. One of the parts of our business model really is providing services to help you do that and to extend the feature sets in our open source tools and to also work on other open source tools. We do a lot of consulting as well as training, webinars, and other things. In terms of data, we work with a lot of different data. I myself work mainly with scientific data sets. We really kind of classify them into 2 major types. We have stuff I work with a lot on the supercomputers is a small number of very large data elements. So each data set that you might be interested in is terabytes to even petabytes in some cases, but there are not very many of them, and you may not keep them for a very long time because they're obviously hard to store. And these can be things like computational fluid dynamics simulations, where you want to visualize these quite dynamically, and then you can throw them away and do something else in the future. Cosmological simulations, trying to understand how the universe evolved. And then we have the other type, which is what I do in chemistry a lot, which is a lot of small records. So 3 million compounds, 40 million calculations. Each record is relatively small, but in total, I think it's about 0.5 petabyte that we're looking at right now with Harvard on the Clean Energy Project. Then there's things like social media data, financial data, and other things you might be more familiar with. And really, depending on the kind of problems we're trying to answer, we have a very different approach to dealing with data, and we need to use very different strategies. When there are a lot of small records, one of the major things we have to look at is how do we index the data, how do we make it searchable in an interactive way, how do we help the user find some meaning in the large numbers of small elements. And then once we've found that, how we can generally just send the data straight to the browser and then visualize it in a web client using JavaScript, and we don't have to do very much on the server side. And in that case, aggregation and summarization become much more important than the data reduction and the rendering, which is stuff I generally do. Then we have the other side where we've got a few very big records, or sometimes you can have a large number of very large records. And you have to think a lot more about data reduction before you send anything to the browser. So if you have a computational fluid dynamics data set, and you're talking about terabytes of data, and the user still wants to be able to look at this in 3 dimensions, then you've got to help reduce that data, and you either stream images to the browser, and you might be controlling a whole supercomputer, or you reduce the geometry to something that's more manageable, and as they zoom in, we can use things like level of detail to help them see the detail as they get closer and closer to specific parts. So for us, when we look at this, we kind of look at the problem and the domain we're looking at, and then we figure out where we're going to store the data. Is metadata going to be stored with the raw data? How are we going to index it? Are there existing metrics that we can use to provide search criteria? What kind of visualizations are interesting? And then, do we want to drive further calculations and simulations, or are we looking at static snapshots of things that have already happened? A lot of the time as well, we have to look at the total amount of data. Does it all need to be kind of on the same site, or can we store some of it in a large data storage facility and then keep more of it closer to the client? And then we've got whether there are actually existing extraction techniques, or do we have to come up with brand new techniques? What is the data going to look at like, and what kind of schemas can we use? Is it well structured? And are there existing ways of indexing and searching? Once we've figured that out as well, it becomes a question of what will it look like when we've got a result? So are we going to display a network to show the relationships? Or is it a 3D volume? Or is it a geometry? Or is it an animation over a time series? And things like, yeah, can we just show them a simple ordered list? Or do we need to show something that's more complex, like a linked list? Or multi-dimensional outputs of scatter plots and letting them zero in on the most interesting data? With big data, we don't actually have a lot of data warehousing at Kitware, so often this is off-site. We work with clients and institutions, and they're the ones that generally have the large data storage. So moving the data is extremely hard, so we tend to work very hard on things like client-server architectures, both on the desktop and on the web. And I'll talk about a few of the frameworks. And then we look at what metadata do we want to extract, and can we make it easy to extract more metadata in the future? Can we back everything up, or do we just want to back up the metadata and then leave the other data that could possibly be even regenerated, depending on whether it's simulation data or data that's been recorded? And then, yeah, we really kind of end up working with the individual client on where the data is going to be and what access we can get to the clusters where the data is housed, and what kind of facilities they're willing to provide in terms of Hadoop or processing locally. The main frameworks that we work on, a lot of the time, I work in C++, so it's quite low level. We use VTK in many different applications, and it's divided really into a set of different capabilities. So we have things like filtering, information visualization, three-dimensional widgets to help you interact with the data, volume rendering, which is often very important in scientific data rendering. And it's all cross-platform. It works on Windows, Mac, Linux, and more recently we're pushing this onto mobile phones and into things like WebGL. And it's wrapped in Python, Tcl, and Java, so it's very easy to access the algorithms we write in C++ from simpler languages that are easy to write glue code in. And most of the time we spend thinking about how we turn the raw numbers that come out of the simulations or out of the measurements we take into three-dimensional data sets and giving them meaning and allowing the person to really kind of interact with the data as it comes out, or to take snapshots and to record movies to then be able to show to other people after the fact. We have a hybrid approach in VTK where the compiled core is C++. It's where most of the algorithms are implemented. And then we use interpreted languages as glue so we can more easily generate new prototypes very quickly. And the interpreted layer itself is automatically generated, so there's no real overhead right now. All of our C++ API is wrapped as soon as we write it. We can wrap it in the languages. We typically have, we have pipelines. So you can see there's usually a data source. So this can be a live source, or it can be a file, or it can be a simulation that's running right now. And then we turn that into data that can be recognized by VTK. We can apply various filters, and you can split the data, you can recombine it. And at the end, we have things called mappers, and these turn whatever data is remaining back into some kind of visual artifact that we can then display on the screen. And then the actors take care of rendering these things onto the screen. And I'll show you a little bit more about how we've then turned these into things that are a little more concrete for the web as well, so you can use this same framework. Paraview then builds on top of VTK. It's another open source project, paraview.org if you want to take a look at it. And it's a parallel visualization application, and it's really a turnkey wrapper around VTK to give you an end user application, because VTK is really a set of software libraries and Python wrapped API. But if you want to install something and quickly work with your data, then Paraview is a thing that people can pick up, they can install, they can download a binary, and then they can really kind of look at data, and they can look at it in massively parallel situations. So we've been used on some very large simulations like the 1 billion cell asteroid detonation simulation, where they wanted to see if Armageddon could be real, and we could really go up there and blow up an asteroid. And then some things that may be a little more useful, like the weather simulation data, where we're trying to understand large weather simulations and help people work with these interactively. One of the major challenges here is that the data is so large, and if you want to interact with this in any kind of non-batch form, you have to control a massive number of nodes in a supercomputer to be able to allow a person sat on a laptop to visualize this and to process the data and be able to see the results of things like filtering in real time. So we build a platform which is entirely client-server based, and we can do separated rendering. So Paraview itself has a client that sits on your laptop, and then it has a render server and a data server that can be entirely remote, or they can, again, run on your laptop if it's a small problem. And we can even split up the rendering job, so if the data is so large it cannot fit on a single machine, we can actually render pieces on as many nodes as we choose to, and then we use the depth buffer for three-dimensional data to then recomposite that and give you a full 3D image. And that's how we're able to achieve real-time visualization of extremely large individual data sets for things that could never fit in memory on any kind of modern machine. And we've used things like Titan, which is the second largest supercomputer in the world, to control segments of that machine just for visualization. So you can literally sit on your laptop and you can control thousands of nodes from an application that is logged into that machine. And you can be using, I think we've demonstrated up to a few 100,000 nodes in some of the big test runs. So it can scale to pretty large data. And then the other side is powering massive tile displays. So if you have three-dimensional data and you have all this density of data, some people want to get as many pixels as they can. So they have these 10 by 50 video walls. And we can do distributed rendering to render the entire scene across hundreds of displays. And we manage the viewports so that you can get each machine to render the piece of data that's relevant for that particular screen. And you can have several servers powering several displays each. And the same goes for things like cave systems, where it's a little bit more complex, but you can wrap the scene onto a cave, and you can do things like stereo, and you can do head tracking. So you can really kind of get inside your data, and you can begin to have insights into very complex data that is very difficult to understand. And it's all in this big open source framework, which is used by a lot of these kind of large visualizations. And then going totally in the other direction, Tangelo is a more recent application with a framework. It's built in Python on top of Cherry Pie. And this is really aiming at when we want to build new web applications, and more now, we're finding requirements from clients and from labs and scientists and people in industry where they want a very quick web application. They don't want to wait too long to get it up and running. They want to see results. So we've got this nice architecture that's HTML5. It's developed with a nice, clean separation. So you have the application and the application logic. So most of the stuff that's delivered is all HTML and JavaScript and CSS. It's fairly static, but you can obviously update this and then refresh. And then you have all the services, and the services are all in pure Python. And if you notice, all of our C++ code is wrapped in Python. So we're able to leverage virtually everything we've done for the desktop via this in Python, as well as the standard Python frameworks and the standard JavaScript frameworks. So we have things like Bootstrap and D3 built into this. And they can just be very quickly used to provide web visualization. And then we can take advantage of Paraview Web, which I'll describe a little bit in a minute. And Paraview Web is using the client-server architecture, but then delivering, instead of to a desktop client, to a web client using JavaScript and WebGL, or we can do image delivery. So if the data is very large, it's actually easy just to deliver the rendered image, which is rendered on a remote server and then pushed out to the client. And this really makes it extremely easy for us to develop a web app. And every service that we deploy is a RESTful API, and it's just a single file. So if I want to add a new service to my web app, we add foo.py, and that provides the service foo. And the service foo can be called from a browser using the JavaScript clients, or we can call it from the desktop. And the desktop, again, we understand JSON. We can use that same language. So we can do very rapid prototyping, and we get the full power of Python in the web services. So we don't really have to worry too much about wrapping stuff because it's already wrapped, and then we can call all of this code and make use of it very, very quickly. And then one of the other things that kind of happened in parallel slightly before this is Paraview Web, which didn't really tackle web services, but it did tackle how how do we expose this massive parallel visualization framework to people on the web? Because not everyone wants to install a client. The client can be complex. It's a very general client. So we want to be able to provide very targeted, very simple interfaces for scientists, engineers, as well as normal people in the world that just want to see things like medical data sets, or they want to see network visualizations. And we can do all this using Paraview Web and now VTK Web, which is an even more cut down version of Paraview Web. But we can then give you a very rigid workflow, and you can define this largely in JavaScript. You use our Python wrapping again to define most of the data flow, so you do the pipelines. And then the framework is really there to give you a 3D web application very, very quickly. And we can do things like geometry delivery and then use WebGL. We can do image delivery, and we can use everything that we can do on the server side. The main constraint there is that you need a server that's powerful enough, or if you have a cluster, you can have a visualization cluster that can then do all the remote rendering. Then it can push it out to the client. So you can do very advanced 3D visualization. And you can do advanced 3D visualization, deliver it to clients that would take gigabytes or terabytes of memory if you have it available on your cluster. Then smashing it all together, Tangelo can use Paraview Web, and we can expose Paraview Web as another service effectively in Tangelo. And Tangelo takes care of launching Paraview Web sessions, so it needs to start up a real process on your server. It needs to keep that alive while the user is interacting with the 3D scene. And then when the user goes away, we need to kill that process and get rid of it so that we don't run out of memory and starve. And we can also then coordinate using multiple servers on the back end if we want to, using the Tangelo framework. So a few simple examples. Flickr metadata, it's openly available, so we often look for good data sets that we can share with people. So it's very easy and very quick to effectively ingest a lot of Flickr metadata, put it into a Mongo database, expose a very simple web service using this Python service framework. And you can go and play with any of these demos. It's,
Marcus, just a question. How easy it is to integrate with BI tools, for example, Tableau? If I have a Tableau dashboard and I want to embed Paraview into Tableau dashboard, but also interact with Tableau dashboard, like pass parameters from Tableau to Paraview through the query string, and then filter the data within Paraview.
If you can put it into a web page and push it through Python, it shouldn't be a big problem. But I've not done a lot of Tableau integration, but we do work with things like D3 and Vega and Bootstrap, and so I wouldn't envisage any major problems, but it's not something we've done in the past.
Tableau has a JavaScript API.
Yes, you should be great. Yeah, if you can use the same JavaScript API. We push many JavaScript frameworks together, depending on what work we're doing, and it usually works very easily.
There's no licensing involved, right?
It's all, I think this is all Apache, so it's Apache v2, but it's, again, very liberal license. Everything we do is usually either Apache or BSD. So yeah, you can look at these demos. These demos are all online, so you can go play with them now. They're live. This is just a lot of data in MongoDB, so we're using PyMongo to retrieve the results through this little Python file that provides a service. And then there's a D3 layer over Google Maps. So a lot of that work, we collaborate with D3 developers, so we've been able to extend this in places and work with them to add new features. And going back to our business model, we can help you customize this stuff, and that's really why it's free. I mean, we're providing the more advanced solutions for people that can't just get this working out of the box. But we do support our open source products, and we have a staff of people who can help you with that. Another one is Enron. So it's a nice set of social media type data that's well understood now. But Enron.py retrieves the emails. It computes the graph structure in Python, delivers it to D3 via JavaScript using a RESTful web API call. And then you can control things like email by time, email originator. So you can try and understand and dig down into the network data to see what might be of interest to you. And this kind of goes back to the first talk a little, but is obviously on the simpler side of what that's doing. Bitcoin was another fun one. It was part of a challenge by DARPA, where we turned up and they had several data sets and they wanted us to try and make sense of them. So again, we're using this Python framework. We're digging into the data on the server side, reducing it down as much as we can in Python, possibly using C++ wrapped APIs. Then producing things in the browser like this intensity histogram. And you also have a detailed plot with the individual transactions. And you have, I don't know if you can see them, but the tooltips, they're a little tiny, but they're all kind of part of this web framework that we can deliver. And these demos, they were developed in like, I think this was less than 2 weeks because that was all the time we had, but it was very quick to prototype. For larger projects, the informatics stack we have is fairly complex, and we can kind of pick and choose the pieces that make sense. We don't use all of the things for every project. We've developed a set of frameworks that can collaborate very easily. We have things like digital pathology, so we're working with Harvard, and slideatlas.org is a live demonstration of this technology. MongoDB is used for these image tiles, and you can really kind of zoom in and out, and this is looking at pathology of cells and slices as you go through. It's an interesting data set. I'd encourage you to have a play with it, and again, this is great kind of medical application of this technology. Arbor is looking at phenotypic trees. So we're trying to understand with the NSF and the University of, I'm going to get the name of the university wrong, so I'm not going to try. This isn't one I work on personally very much, but I've helped with things like this, this visualization, which is fully interactive in C++. You can also push it out to a D3 display that looks quite similar. And you can see relationships. So you can see like the blue solid line is a character trait that is shared by many of these species. And then you can look at the tree on the side, and when you have the interactive view, you can really then kind of zero in on the pieces that seem interesting and filter out the rest. So it helps you see these larger patterns. And it's just one view of the data that you can take, but we often look at this multidimensional data, try and reduce the complexity down as much as we can. And then cosmology is another interesting area. I haven't done a lot of this, but we're looking at simulations on supercomputers as well as observations. We're trying to understand how the universe evolves. So we have a lot of libraries we've developed with some of the best scientists in the world, like Argonne National Lab and Los Alamos. And we're helping them find things like halos and caustics so they can understand the evolution of the universe as they run these large-scale simulations on some of the biggest supercomputers out there. And this is all through Paraview. And again, we're developing web frameworks to make it easier to share this data with members of the general public. Climate data, there's a lot of controversy around it, I know, but we've been trying to help make this easier and more transparent. So there's the ultra-scale visualization and climate data analysis toolkit. I don't work on this at all, but I know a little bit about it. But it's largely a very collaborative effort. It's led by Lawrence Livermore National Lab. We're one of the subcontractors that does a lot of the engineering. And we're looking at integrating a lot of the climate modeling data as well as the measurements that have been taken. And this integrates a large number of libs as well as kind of R stuff, like VTK. There's R, D3, 3D, CDAT. But you can see the scale of the data they're looking at here and tackling it with the same common tools. Right now, they have around 3.5 petabytes, but the next generation of data is growing to something between 350 petabytes to around 3 exabytes. And they actually mirror this around the world, and we're developing libraries to kind of help analyze this. And you obviously have to be very careful about where you reduce the data and how you move the data around, and you don't want to waste too much of that bandwidth. And we're developing tools to really help you do this so you can understand things like time evolution as you look at climate modeling. Massive video walls so the scientists can really kind of understand each one of those squares is a large screen. And then this is a time series as you move through on a projection of the flat Earth. So you're trying to understand how the climate changes over time and help scientists kind of really dig into these 3 petabyte data sets. And they want to do it interactively. So you can do some stuff in batch, but you'd still need to do some of this interactively using a large number of nodes. And then my stuff is chemistry, and I'll zip through this because I'm running a little short on time, but developed a set of applications. We're really looking at how scientists can generate the data, run the simulations, and then make sense of the informatics that comes out. So we have a lot of data exploration. We leverage things like Qt, VTK, MongoDB, OpenBabel, and many other tools. We do things like multidimensional analysis. We have the molecular graphs. So we do a lot of things like similarity searches. So we want to, a scientist will find a molecule that's interesting, then they want to find every other graph that is similar to that graph. So you can see why this is applicable more generally as well as to chemistry. again, moving MongoChem to the web, it was a desktop application, still is, but there's a lighter weight client, and it builds on this same set of frameworks. So instead of me having to do all this work from scratch and take months or years, I was able to just pull this into, we were already using MongoDB, but we can add the RESTful APIs using these Python files. We can use VTK Web and Tangelo, and then we can do a lot of processing right next to the data and then just send it to the web client. And it uses the same interaction. It uses the 3D rendering from VTK, and you have a nice kind of searchable view that anyone can play with from the web, and then you can look at the same data in a richer desktop client that's developed that has more power and more processing power, and raw OpenGL that you can do locally. MongoDB for a lot of our projects has been useful. I mean, we obviously look at other things, we use other things, but it's nice in that it has good C++ drivers, it has good Python drivers, it's fairly agnostic there. It has a nice document structure for us. We can access the JavaScript to use MapReduce, which isn't as great as it sounds because you've got a lot of text translation. But it also has things like GridFS, so it can efficiently store large binary files when we want to do that. And it maps very well between JSON for the web and BSON for a binary representation, which is used internally. And we can push this back and forth very quickly, and they actually just memory map their database. So what you get when you retrieve a query is just a stream that comes straight from the memory mapped file. Yeah, the data in open chemistry tends to be small, on the order of megabytes for the individual records to maybe a few gigabytes for very large simulations. We're looking at extending this to materials as we look at more and more large materials, but the institutions generally maintain the disks. The Clean Energy Project is a great example here where IBM is providing the World Community Grid. We're using volunteer resource to do the calculations. And we're doing high throughput in silico studies to find the best organic photovoltaics that we can use. We've partnered with several groups, and we're able to kind of look at simple numbers for a lot of different properties in the web client, and then we can do 2D graphs and then 3D structure to look at how these different shapes interact with one another. And you can look at the main site there. The data itself, there's 2.3 million unique molecules. That's what we ingested. 22 million conformers, so they're just different poses of the same molecules. So there's 22 million in total. There's 150 million individual calculations, and it's around 400 terabytes of data. But the interesting metadata, it takes a long time to extract, but it's only actually 80 gigabytes of real metadata that the scientists are all that interested in. We have to do that in batch, but then it becomes very interactive to search this and manipulate it and interact with it and drill down. The next set, it grows around 1 terabyte a day, but the next set is around 2.8. I think it's actually grown to 3 million now, so I should update these. And around 0.5 petabyte, 0.6 of a petabyte. One of the really nice things about this, it's part of the Materials Genome Initiative, but the data is CC by SA, so it's a very good data set to kind of drill down in and use as an experimental data set. It's openly licensed, and we can really kind of fit it into our current model, which is 1,024 atoms or less. We use that for a lot of the descriptors to give us a unique identifier for a particular molecular graph. So we need some way of seeing if one molecule is the same as another, and right now we're limited by the identifier that we're able to generate. Kitware itself builds communities around these projects as well, so we don't just sell services to companies, we often take contributions from people around the world. Some of them are paid, some aren't. Some of the customers we work with also develop the code with us, and we do a lot of promotion like this as well, coming out and talking about what we do. But I think shared frameworks are really needed to help work with the data. We didn't develop all of these things, and there's a lot of us at Kitware that have different specialties. But we're developing a lot of tools to help you really kind of store and share and publish the data and look at different ways of analyzing the data and making sense of it. And semantic data is another important aspect I didn't really get into, but it's something that I think is going to become more and more important over the next few years. And that's pretty much all I had for you. So thank you for listening.
Any questions?
Sorry.
Testing tools you have used in your projects, like JMeter or tools, how do you? Because it's a distributed testing is a challenge, right?
Yeah, we do a lot of work on software process. So we develop CMake and CTest and CDash, which is a dashboard which gives you a traffic light system for seeing when things are passing or failing. We use Git for version control. We use Gerrit to do online code review. We use mailing lists and bug trackers. So we have a lot of machinery around that. I could give you a whole half-hour talk on.
Well, they're more, SCM, source code. I'm talking about more quality testing tools.
That would be C-Dash, which is one of the things we develop. It's open source. And C-Test, which does the actual testing. So we do things like code coverage using Gcov and Dart, Bullseye, sorry. We use Selenium for some of the web applications, and we feed this into C-Dash, and C-Dash is basically
I'm talking about more performance testing,
Which kind of performance testing?
So in your case, was that latency or scalability?
Right. So we do image-based regressions to make sure the images are correct, and then we do have baseline measurements on timings, and we often do optimization where we need to, and that can be a variety of tools. I mean, a lot of this is parallel, so it can be fairly involved when you have to debug it. But we use things like MPI and CUDA. So the tools really vary depending on, like OpenGL again has its own set of debugging tools, but we use a large array of tools. I'm not sure I can really go into any detail unless you have a specific area you want me to.
I'm mainly interested in performance testing,
I think we have tried out some tools like SoapUI and LoadUI. Those are free to use, open source.
Right, I'm familiar with SoapUI, so, but I think it's, the challenge is in terms of giving you the, JMeter, for example, is more popular than SoapUI and stuff like that. But when you have a data set which is larger than 2 gigabyte,
Yep.
Java has a bug in it.
Oh, we don't use Java very much, so Java I can't tell you about because I don't really program it.
People have done, if you look at, if you do Google it, open source
Yep.
AWS, basically you're generating load and you are hitting the server and you're having a huge amount of data. That's, the test data, the result data, which you want to aggregate and present it, right? That itself is a challenge. In fact, MR, you can do an MR reduce on the test data you collected.
Yep.
Then you can do, for example, I'm actually looking at a tool called Query.io, which, you do a MapReduce job and then you get time series. So once you have MapReduce and then you can get all kinds of information about the test data you collected,
Yeah.
So, I'm looking for something like that, basically. Yeah.
I mean, all of our core algorithms are C++. So we use C++
I'm not
tools.
talking about functionality, I'm more talking about the load testing, performance testing. I know there are a lot of white box tools,
Yeah.
All of those tools you said I'm familiar with.
Right.
Yeah, that's okay. I just don't know. Because this is a distributed testing. The performance testing is a big chapter.
Yep.
Okay. So I don't see anybody covering that in any of the presentation. So.
I mean, Paraview itself has some tools that do the timings and diagnostics as we run across thousands of nodes, and it looks at things like memory load and timings. And so we have some of that built into our core algorithms, and we can turn it on to get debug traces, and then we can visualize it ourselves. And that's when we're running on thousands of nodes, for example. But yeah, it's a very loaded question because there are very different types of load profiling you might want to do, whether it's a single application running in one thread or 1,000 running across a few 100,000 threads.
Yeah, you could also do some, see whether your system is linearly scalable. So you don't need to test all of them at once. You could test in a single entity or a unit.
Yeah, and we often become I/O bound because the data is so large, and so the CPU time is relatively negligible because it's the I/O performance that's hurting us more. But yeah, it's a fairly involved area.
Thank you. Anyway, I don't want to hold. People wanted to leave, I guess.
It is late.
Any more questions? Well, I want to thank you
Thank
for
you.
coming here, all the speakers. We really enjoyed the presentations. Once again, this is your meetup. If you want to present, know someone that wants to be here or wants us to invite someone, just let us know. We will be happy to bring them. And topics as well. I saw a few comments today about topics. We will try to incorporate those topics into next meetups. Hopefully we will have the presentations available on our website next week, and we will upload the videos as soon as we have them. And let's thank our speakers for a great presentation. And I hope to see you in our next meetup.